Welcome to video 7.3 on the VSEPR theory. In this video, you're going to learn how to explain why certain molecules have certain shapes. Then you're also going to be able to determine the molecular geometry of molecules given their Lewis structure. So this video, you're going to learn new shapes that we use in chemistry. The key vocab terms we're going to look at is VSEPR theory, hybridization, and hybrid orbitals. So as we get started, you're going to want page 202 in your notes, and then of course your periodic table, pencil, and notes. So get ready as we deal with the VSEPR theory. So when we look at molecular geometry, this whole idea is we start with our Lewis structure so that now we can begin to see how a molecule actually looks, the shape of it, the geometry of it. And so atoms take certain shapes based on the idea of what their electrons are doing. So the valence electrons around that central atom are going to repel each other as much as possible. Remember, a law of the universe, opposites attract. So here I have electrons, here I have electrons. To be exact, I have a double bond, which means there's 4 electrons here, double bond, 4 electrons. And so these electrons are going to push away from each other as much as possible and to create what we're going to call a linear shape. Here, this example, we have a double bond, double bond, double bond, which means 4, 4, and 4 electrons. And so these electron-dense areas are going to push away from each other to a point where we're going to get an equal split of 180 degrees, 180 degrees, and 180 degrees because these electrons want to get away from each other as far as possible because likes repel each other. This is our VSEPR theory. Valence, shell, electron, pair, repulsion. So the main idea here is why do we believe this molecule has this shape is because the electron pairs are going to repel each other. So as we do this, we're going to be looking at the central atom and we're going to be looking at number of electron dense regions. So again, this is all based on the central atom. And it's all going to be based on how many electron-dense regions he has around him. This carbon has 1 electron-dense region and 2 electron-dense regions. This sulfur has 1, 2, 3 electron-dense regions. So once we begin to identify electron-dense regions by either pairs or lone pairs on the central atom, we will use a chart like this to be able to identify the actual name and shape of that molecule. So eventually you're going to have to be able to draw the Lewis structure and then be able to identify the shape, and eventually I'm actually going to have you even draw these shapes out. So what we're going to do is, based on our Lewis structure, we're going to count up the number of regions of electron density. Again, this could be bonds or lone pairs attached to the central atom, and then we're going to use our chart to determine the electron geometry. I'll give you some practice problems on this in a second. But real quick example, if I look here, my oxygen, carbon, oxygen, my central carbon has 2 regions here, 2 bonds. So I go here, I find something that has a 2 electron dense areas on it. And so therefore that would be called linear. The next one, this guy has 3, 1, 2, 3. I look at my chart. 3 electron dense regions is going to be a trigonal planar. But when I get more specific, I see that it has actually 3 atoms bonded to it, or 3 bonds. This one has 2 bonds, but 1 lone pair. And so we're going to go with this one and call this shape trigonal planar. So we will be using this in a second. Make sure you get this on page 202 in your notes to look back at it. So what's going on here? Well, this idea is all about the repulsion of valence electrons, and which is why we get these different shapes. Now, the different electron-dense regions will behave differently, meaning if something is in a bond, it will have a different influence than if something is just in a lone pair. So look at this guy right here. This is a lone pair of electrons. These are 3 single bonds. This lone pair is going to have more influence. It's going to have a greater electron density than these bonds here, and that's going to influence the shape and push these hydrogens down. Here, like in water, we see 2 lone pairs. And so this is going to create an overall more electronegative dense area, which will push these electrons down even more because there's a little bit of positivity here from the hydrogens. And so again, all we're seeing here is that they're going to spread out, but why we get different bond angles is because these lone pairs have a greater negativity, which will push these bonds down slightly more. And that'll come more into play when we start to identify and understand these bond angles. One quick word on this idea of hybridization. So first of all, this whole geometry is based upon what we call hybridized orbitals or hybridization. When you think about the word hybrid, think about the car industry. Hybrid cars run both on gas and electric. So when we talk about hybridization, what we're doing is we are actually going to combine our s and our p orbitals. Think back to our electron configuration. We know that the octet rule is based off of 2 electrons in the s and then 6 electrons in the different p orbitals. Well, the way we explain these shapes is that these s and p's become hybrids. And so what we used to think as just an individual S and an individual P, or in other words, a circle and then a dumbbell, they come together to form 2 dumbbells to hold those electrons. So this isn't really a big focus. It's just kind of something we want to mention so you start to hear early on in chemistry. But hybridization is this idea that the S and P orbitals begin to morph together and create new shapes. And these hybrid orbitals create equal energy levels for our new S&P sp2. So not a big deal, just the major idea is that we are blending together our S and the P, or our SPP or SPPPs, to create new individual orbitals. So here we go. Let's get down to the nitty-gritty. What you're going to be doing on this homework assignment is you're going to be drawing your Lewis structure, and then based on that Lewis structure, use this chart to identify the new name or the molecular geometry. And then eventually I'll actually have you draw these out yourself. So here we go. Let me give you a practice. I'll show you the first 2, pause the video, and then you can try the last 2. So first of all, I want to draw my Lewis structure for carbon with 4 hydrogens. We've already done this a lot, so I'm going to jump ahead and call it CH4. So now I need to identify how many electron regions does it have around my central atom. I have 1, 2, 3, 4. So there are 4 areas around that central atom. So now as I look on my chart here, I look for what has 4 regions around the central atom. I see the 4 is here. And so overall, this is going to be some form of tetrahedral. Now I need to see, what are the 4 things bonded to that central atom? Are there 4 elements? Are there 3 elements and a lone pair? Or are there 2 elements and 2 lone pairs? In this case, I have 1, 2, 3, 4 elements bonded. So we're going to call that a tetrahedral. So again, a quick recap. The X's stand for elements. The dots stand for lone pairs. You just simply match up what you got to here to come up with the name. Let's do it again with our NH3. So NH3, I'm going to draw it out, my hydrogens. And again, I'm just kind of showing you guys quickly what you've already learned. So really, it's just going to be this. Now I want to count up how many electron-dense regions do I have around this nitrogen? I have 4. 1, 2, 3 that come from bonds, and 1 area that comes from a lone pair. So as I look on here, I got 1, 2, 3, 4 things around my central atom. So now which one does it look like? It doesn't look like this one because this has 4 elements around the central and I only have 3. So we're going to go to what's called trigonal pyramidal. We'll just call it trigonal pyramidal, right? Because it has 3 things bonded to the central atom and 1 lone pair. Water, draw it out. Again, we've already done this a lot. Go ahead and pause the video now and see if you can identify, based on this, how you would name that. All right, welcome back. Water has 1, 2, 3, 4 things around that central atom. So again, I'm still in this row of the table. But now I have 2 elements and 2 lone pairs. 2 elements, 2 lone pairs. So I'm going to call this bent. Some people call it angular. I like the word bent. This last one, try it yourself. Pause the video, draw your own Lewis dot structure, and then come up with the name. Give it a try. Seriously, this is good practice for you. Okay, welcome back. If you would have drawn this, you would have saw that fluorine, there's 6 of them. And so what we're going to get is an expanded octet around sulfur. I have my 6 fluorines. Again, to be diligent, we want to draw our lone pairs here. Sometimes professors will get lazy and they'll draw little lines here to mimic a lone pair. Again, you need 3 lone pairs on all the fluorines, but that doesn't really matter for what we're doing. What we're doing is looking at the central atom. The central atom has 1, 2, 3, 4, 5, 6 bonds around it. So what's something that has 6? This is going to be my octahedral. Overall, it's called octahedral, but which one exactly am I looking at? And I want to look at the first one because I got 1, 2, 3, 4, 5, 6 things bonded to that central atom. So this last one would be called octahedral. Again, eventually, I'm going to actually have you draw this out where you're going to use triangles and lines to demonstrate the idea of how these X's are jumping out at you and these X's are going into the page and these are in the Z-axis. We'll look more at this in class with some model ball sets. But again, this is a crash course in the understanding of molecular geometry. So, as we start to wrap up, VSEPR theory is all about how the electron pairs repel each other. Some electron pairs will be lone pairs, some electron pairs will be in a bond. And this is the idea that these electrons will repel each other as much as possible. So they're going to want to spread out, whether it's a lone pair or bonds, they're going to want to spread out as much as possible. And then based on that information, we can now identify the geometry. So the geometry is just based on the number of areas of electron density around that central atom. I hope, again, you have a great day and you're enjoying this part of chemistry. Have a great evening.